things drifting along like cotton candy, and you think, well, that's about the lightest thing in the world. That's a puff of nothing. A wisp, a bit of mist that wandered upward and forgot to come back down. That's completely wrong. And I can show you why. A single one of those pretty white cumulus clouds, the ordinary kind, the kind a child draws with a crayon, weighs about 1 million pounds. Let me say that again. One cloud, 1 million pounds. That's roughly the weight of 500 automobiles, floating above your head, right now. And the big ones, the thunderheads, those towering monsters that go dark at the bottom and flash with lightning, those weigh millions of tons, plural. We're talking about the weight of a small city hanging in the air, held up by what holds it there, because if you dropped 500 cars from a mile up, they wouldn't float. They'd fall. Everything heavy falls. So why doesn't the cloud? That question, once you take it seriously, once you stop just looking at clouds and start thinking about them, opens up one of the most beautiful little puzzles in all of physics. And the answer involves some ideas that you'd never expect, ideas that connect the tiniest things in nature to the biggest things you can see. So let's begin with what seems obvious and see how far it gets us. But you look at a cloud and you say, well, it's made of water vapor. It's steam. It's gas. Gas is light. Gas floats. End of story. That feels right, doesn't it? You boil a pot on the stove. The steam rises. It disappears. Water becomes gas. Gas goes up. Clouds go up. Clouds go up. Simple. But there's a problem. Clouds are not made of water vapor. Not really. Water vapor is invisible. You can't see it. Right now, in this room, there is water vapor in the air. You're breathing it. You don't see it. The air between you and me is full of water molecules bouncing around as gas, and they are perfectly transparent. If clouds were made of water vapor, you wouldn't see them at all. They'd be invisible. That white puffiness you see is not gas. It cannot be gas. You know this because you can see it, and water vapor is as transparent as the air itself. So, what are clouds actually made of? They're made of liquid water. Tiny, tiny droplets of liquid water, suspended in the air. When meteorologists go up in airplanes and fly into a cloud and measure what's there, they find water droplets. Real liquid water, not gas. The water vapor has cooled down and condensed back into liquid, just like the moisture that appears on the outside of a cold glass on a humid day. That's what a cloud is. It's a collection of water droplets so small you can't see any individual one. But there are so many of them, trillions upon trillions, that together they scatter sunlight and make that white fluffy shape you see from the ground. And here's another thing that's quite surprising. These droplets don't just form out of nowhere. Pure water vapor actually has a very hard time condensing into droplets by itself. If you had perfectly clean air with nothing in it but nitrogen, oxygen, and water vapor, you could cool it well below the normal condensation temperature, and the vapor would stubbornly refuse to condense. It's a strange fact. The problem is that forming a new droplet from scratch requires building a curved surface of water, and surface tension makes that energetically unfavorable when the droplet is very small. So nature cheats. Every cloud droplet forms around a tiny speck of something. A grain of dust, a bit of sea salt carried up from the ocean by the wind, a particle of sulfur from a volcano, a speck of pollen or soot. These are called condensation nuclei, and the atmosphere is full of them, billions of them in every cubic meter of air. When moist air cools down, the water vapor grabs onto these tiny particles and condenses around them. Each cloud droplet is, in a sense, a tiny ball of water wrapped around a speck of dirt. If the air were perfectly clean, we'd have far fewer clouds. By the way, at high altitudes where the temperature is well below freezing, the cloud is made of tiny ice crystals instead of liquid droplets. Those thin, wispy cirrus clouds you see very high up, those are ice. But the principle is the same. It's still condensed water in solid or liquid form, not gas. Now, if they're liquid water, that changes everything. If they're liquid water, that changes everything. Because liquid water is heavy. You know how heavy water is. Pick up a bucket of water sometime. A gallon of water weighs about 8 pounds. Water is a dense substance. It sinks in almost nothing. And the cloud is made of it. So the first thing we need to do is figure out how much water is actually up there. And to do that, we need two numbers. We need to know how big the cloud is, and we need to know how much water is packed into each little piece of it. Let's start with size. How big is a typical cumulus cloud? Well, people have measured this. You can do it yourself roughly by driving underneath a cloud on a sunny day when the sun is directly overhead. The shadow of the cloud falls on the ground, and if you know how fast you're driving and how long it takes to cross the shadow, you can figure out the width of the cloud. Scientists have done this carefully, using ground observations and aircraft measurements. A typical fair-weather cumulus cloud, nothing special, just one of those pleasant afternoon puffs, is about 1 kilometer across. That's a little more than half a mile, and it's roughly as tall as it is wide. So we can think of it very roughly as a cube, about 1 kilometer on each side. Now, 1 kilometer is 1,000 meters. So the volume of this cube is 1,000 times 1,000 times 1,000. That's 1 billion cubic meters. Already the numbers are getting surprising, aren't they? You don't think of a cloud as being a billion of anything. But there it is. 1 billion cubic meters of space filled with air and tiny water droplets. 1 billion cubic meters. Let me give you a sense of how big that is. An Olympic swimming pool holds about 2,500 cubic meters of water. 1 billion cubic meters is 400,000 Olympic swimming pools. That's the volume of one modest cumulus cloud. And we haven't even gotten to the big ones yet. The next question is how much liquid water is in each cubic meter. Scientists have measured this too using instruments carried by aircraft and weather balloons. They call it the liquid water content. For a typical cumulus cloud, it's about 0.5 gram per cubic meter. 0.5 gram. That sounds like almost nothing. 0.5 gram is the weight of a small paperclip. 1 cubic meter of cloud contains about 1 paperclip's worth of water. That's astonishingly little, and this is part of why we're fooled. When you walk through fog, which is basically a cloud sitting on the ground, it doesn't soak you right away. It feels like nothing much, because there's almost no water in there. It's mostly air. The water makes up less than 1/millionth of the total volume. But watch what happens when we multiply. This is where arithmetic becomes disturbing. 0.5 gram per cubic meter times 1 billion cubic meters. That gives us 500 million grams. Now there are 1,000 grams in a kilogram. So divide by 1,000 and you get 500,000 kilograms. 500,000 kilograms of water in one cloud. Let's put that in a unit you might feel in your gut. 500,000 kilograms is about 1,100,000 pounds. Call it roughly 1,000,000 pounds, or if you prefer, about 500 tons. 500 tons of liquid water floating above your head in a single ordinary cloud. For perspective, a large African elephant weighs about 5 tons. So this one cloud, this innocent puff of white, weighs as much as 100 elephants, stacked on top of each other, if you like, floating. A Boeing 747, fully loaded, weighs about 400 tons. Your cloud is heavier than a fully loaded jumbo jet, and nobody seems alarmed by this. And that's the small cloud, the everyday cloud. There's a whole spectrum of clouds, and they get progressively more alarming as they get bigger. A stratocumulus cloud, those big gray blankets that can cover the whole sky, they're not very thick, but they're enormously wide. A single sheet of stratocumulus can extend for hundreds of kilometers. The total water content of one of those sheets can be tens of millions of tons. And then there's the king of clouds, the cumulonimbus, a big thunderstorm cloud. Those things extend from maybe 2,000 feet off the ground all the way up to 40 or 50,000 feet. They can be 10 or 15 kilometers across. Inside, the updrafts are ferocious, sometimes reaching speeds of 30 meters per second or more, powerful enough to keep hailstones the size of golf balls suspended in midair while they grow. The liquid water content is much higher than in a fair-weather cumulus, maybe 2 to 3 grams per cubic meter instead of 0.5 gram. When you work out the numbers, a big cumulonimbus cloud can contain 1,000,000 tons of water. 1,000,000 tons. That's about the weight of 3 Empire State Buildings. Floating in the sky, making thunder and lightning and dropping hail on your car. Now, I hope you're a little disturbed by this. You should be, because everything about your everyday experience says that heavy things fall. I drop a penny, it falls. I drop a bowling ball, it falls. I drop 500 tons of water, it should fall. It should come crashing down like the most spectacular waterfall you've ever seen. But it doesn't. The cloud just sits there, drifting peacefully. Some clouds last for hours. They hold their shape. They float. What's going on? Well, the first thing people usually say is, the cloud must be lighter than air, like a helium balloon. A helium balloon floats because helium is less dense than the surrounding air, so it gets pushed upward by buoyancy. Maybe the cloud is like that. But it isn't. The cloud is made of liquid water droplets, and liquid water is about 800 times denser than air. 800 times. If you took all the water from that cloud and collected it into a solid ball, just gathered it all up, it'd be a ball about 7 or 8 meters across, and it would be tremendously heavy for its size. If you made a solid ball of water the size of a cloud and tried to float it in the atmosphere, it would fall like a boulder. There's nothing buoyant about liquid water and air. So it's not buoyancy in the simple sense. The cloud is not lighter than air. The water in it is much heavier than air, and yet it stays up. This is where you have to stop and think carefully about what's actually happening inside a cloud, because the key is not the total weight. The key is how that weight is distributed, and it's distributed in a way that changes everything. Remember those water droplets? Let me tell you how small they really are. A typical cloud droplet has a diameter of about 10 to 20 micrometers. Now, a micrometer is 1/1,000,000th of a meter. So 20 micrometers is 20 millionths of a meter. That's about 1/5 the width of a human hair. You could line up 50 cloud droplets across the width of a single hair on your head and still have room left over. To put it another way, a period at the end of a printed sentence is about 300 micrometers across. You could fit about 15 cloud droplets across the dot at the end of a sentence. These are very, very small things. Here's something fun to think about. If you could shrink yourself down to the size of a cloud droplet, the experience of being inside a cloud would be nothing like what you imagine. You wouldn't feel surrounded by mist. You'd feel like you were in empty space. The nearest other droplet would be, relative to your body size, about 50 body lengths away. It'd be like standing in the middle of a football field with one other person at the far end. You'd barely notice them, and the air around you wouldn't feel like air. At that scale, air would feel thick, like syrup. Every molecule of nitrogen and oxygen would be bumping into you, jostling you, pushing you randomly in all directions. Physicists call this Brownian motion, and at the scale of a cloud droplet, it's a real force to contend with. The droplet is being constantly kicked around by air molecules, trembling and dancing in place. It's a wild, chaotic world down there. Nothing like the serene white puff you see from the ground. And because they're so small, each individual droplet weighs almost nothing. A single cloud droplet with a diameter of 10 micrometers weighs about 1/2 trillionth of a gram. That's a number so small it has no meaning in everyday life. You could put 1 billion of them on a kitchen scale and the scale wouldn't flicker, but there are a lot of them. In a typical cubic centimeter of cloud, there are a few hundred droplets. A cubic centimeter is about the size of a sugar cube. In the volume of 1 sugar cube of cloud, a few hundred tiny water droplets are floating around. Scale that up to the whole cloud, 1 billion cubic meters, and the total number of droplets in a single cloud is something like 100 trillion. That's 10 to the 14th power, 100 million little spheres of water, each too small to see, all suspended in the air. Now, here is where a very beautiful piece of physics comes in. And I want to tell you the idea carefully, because it's the kind of idea that once you understand it, you start seeing it everywhere. There's a law discovered by a man named George Gabriel Stokes, an Irish mathematician and physicist, back in 1851. Stokes was working on the general problem of how fluids resist the motion of objects moving through them. Specifically, he wanted to know what happens when a small sphere moves slowly through a viscous fluid. And what he found is something that seems simple but has enormous consequences. The drag force on a small sphere is proportional to its radius, not to its cross-sectional area, which would go as the square of the radius, not to its volume, which would go as the cube, just to the radius itself, times the speed, times the viscosity of the fluid. That's Stokes's law. Now, this is a little counterintuitive. You might have guessed that drag depends on how big the sphere looks to the oncoming air, which is its cross-sectional area, which goes as radius squared. And for large, fast objects like baseballs and airplanes, that's roughly right. But for very small objects moving very slowly through a thick, sticky medium, the physics is different. The flow around the sphere is smooth and laminar, not turbulent. And in that regime, the resistance comes from the viscosity of the fluid, from the fluid's internal stickiness, and it turns out that scales with just the first power of the radius. There's actually a clever way to see this must be true without doing any mathematics at all. Just from dimensional analysis, the drag force must depend on the viscosity, the radius, and the speed. Those are the only relevant quantities. The viscosity of air has units of mass per length per time. The radius has units of length. The speed has units of length per time. The only way to combine those three quantities to get a force which has units of mass times length per time squared is to multiply them all together. Viscosity times radius times speed gives exactly the right units. So the drag force must be proportional to each of them to the first power. There's no other combination that works. Stokes proved the exact proportionality constant is 6 pi, but the basic dependence, the first power of each, you can get from dimensional reasoning alone. I always find that satisfying, when you can see that a result has to be right just from the units before you do any calculation at all. Now think about what Stokes' law means for a falling droplet. Two forces are acting on it. There's gravity pulling it down. Gravity depends on the mass, which depends on the volume of the droplet. Volume goes as the cube of the radius, and there's drag pushing upward. Drag goes as the first power of the radius. So what happens when you make the sphere smaller? The weight drops as the cube of the radius, but the drag only drops as the first power. If you make the sphere 10 times smaller, its weight goes down by a factor of 1,000, but the drag only goes down by a factor of 10. Relative to its weight, the drag force becomes 100 times more important. Let me put that differently. For a big object, gravity is king. Air resistance is a nuisance. For a tiny object, air resistance is king. Gravity is barely relevant, and the crossover between these two regimes depends on size, and only on size. Same material, same shape, same air. The only thing that changes is the diameter, and the whole balance of forces flips. This is why dust motes float in a sunbeam. This is why pollen drifts for miles on a summer breeze. This is why fine flour hangs in the air of a bakery for minutes after you pour it. And this is why cloud droplets don't fall. Well, let me